So for those who don't know me, my name's Cameron Wilson. So I'm a second year PhD student up in Edinburgh. As you can probably see, it's horrible and grey here, as it usually is here as well. So my supervisor up in Edinburgh is Simon Parsons, and my supervisor down at the CCDC is Dr. Peter Wood. So yeah, as we just said, my project so far has been based around the behavior of occupied and void space in molecular crystal structures at high pressure, and this is based around the CellVol program, which I'm going to be talking about today. So just to give some context for what my project's been based on so far, it's mainly been focused around high pressure crystallography. So when we say high pressure crystallography, we're talking about studying crystal structures under very high pressures, so generally putting them between two diamonds and squishing them together to many thousands of times the pressure you'd see in a car tire. So as you can see here, I've plotted a histogram. So this was done with the nice new high pressure subset. And you can see here that the number of high pressure structures is increasing year on year on the CCDC, on the CSD. And so this sort of gives an idea of the importance of studying how studying these structures is becoming a more significant part of structural chemistry. So just some context. So a crystal structure represents a minimum in free energy, as I'm sure we all know. So under ambient conditions, that represents an optimization between internal energy, so this delta U term, and entropy, so this T delta S term here. But obviously, as we move to higher and higher pressures, this PDV term is going to become increasingly significant. And so almost all high pressure phase transitions are driven by a reduction in this PDV term to, of course, overall reduce this delta G for the particular polymorphic form. And it's been thought more recently in the last few years that a lot of this compression is initially taken up in the void space within crystal structures. And this is because even non-porous crystal structures contain at least 20% void space at ambient conditions. And so the inference there with void space initially taking up this compression is that void space is a lot softer than the network of intra and intermolecular contacts. And so one of the ideas of this sort of process we've been working on so far is sort of defining this difference between the two spaces. So void space in a crystal structure, obviously if you think quantum mechanically, is a bit weird, but from a sort of chemistry point of view, we have to try and sort of define a cutoff from when we define occupied and void space. So I know the Mercury has its own version, the rolling probe, which is based upon putting a probe of a defined radius and grid points across a crystal structure. There's also the Crystal Explorer method, which works with electron density cutoffs. But we've designed a new method for looking at void space, which is based on van der Waals radii. So these van der Waals radii were recently collected by Alvarez in his paper Cartography of van der Waals territories. And this was built up of large searches of the CSD to define sort of these average distances between compounds. And so we define this void space as the area beyond the van der Waals radius of any atom center, with that within the van der Waals radius defined as this network of intra and intermolecular contacts. So this is what we define as our network volume, so our occupied space, as opposed to our void space. And we can think of how this calculation, a simple model for how this calculation works is we consider this sphere within a cube, and if we place points randomly within the cube and then sort of measure up the number of points which also fall within the sphere, we can quickly, through the ratio of these points, estimate the ratio of the volumes as well. And so we can build this model up to look at crystal structures by considering our box being our unit cell and our spheres being lots of individual spheres at atom centers with radius defined by their van der Waals radii. And so using these equations down here, we can see that we can quickly sort of build up a way of calculating this void and occupied space in crystal structures. And it actually turns out that by studying these two volumes separately, we get some quite interesting behavior come out. So this process was recently written and fully coded using the CSD API, and it was written into the CellVol code, as I described before. So this is available from this GitHub page down here. And it was also recently published in this paper here. So this was my first author paper that came out in March, so I was really happy to see that. So you can see here a brief sort of overview of the molecular surfaces you kind of get from this code. So you can see that these are all individual random points that have been defined within the van der Waals radius of atom centers, so the network volume. And you can sort of see as increasing pressure, we increase in pressure, we sort of overlap these surfaces to make a nice big blob. And this actually reveals some really interesting information. So this code, you can run it through the Mercury interface. As you can see, this little video going on down here, and it runs off, so you can get the crystal structure report up at the top here, and also the CellVol analysis at the bottom here as well. You can also run it through the Mercury, also run it through command line, and its input is a CIF, but it can be any of your own CIFs or any published CIFs. You can also, so you can search through the CSD or input any of your own CIFs to that. So within this paper, we used this code to study all the high pressure structures that were suitable. So we filtered out quite a lot, but within the CSD, we looked at all high pressure studies, and we published all that work within the SI of this paper here. When within the paper, we sort of discussed some of the more interesting findings of that study. So I'm going to talk about a couple of them now. So yeah, so when we look at high pressure structures, we often look for phase transitions, and so we can spot those by discontinuities in volume, as I sort of mentioned before. So when we talk about a first order phase transition, we look at a discontinuity in the volume, in the overall volume, whereas when we talk about a second order transition, we're looking at for a discontinuity in the rate of change of volume. So for any first order transitions, they're quite easy to spot normally. So in a unit cell plot like this, we'd normally see a step at the transition, something similar to that. But the high pressure literature does contain a lot of examples of where we see these phase transitions in high pressure Raman or high pressure IR studies, in which the crystal structures, so the sort of unit cells and volume analysis, shows no response of these at all. And so we sort of believe that this might be due to lots and lots of second order phase transitions, in which the sort of classical crystallographic analysis is just not really sensitive enough to find them. But this is where the CellVol code comes in, and it sort of provides a sort of a stepping stone between the macroscopic sensitivity of crystal studies and the microscopic sensitivity of these sort of spectroscopic studies. And a particular example of this is naphthalene. So naphthalene was first discovered that there was a phase transition, and naphthalene was first reported about 80 years ago by Bridgman in his work in the 1940s. But ever since then, people have sort of argued back and forth about whether there is a transition or not. So a lot of the IR work technique generally sees this transition, whereas the Raman doesn't often see it. And it's despite there being 3 crystallographic studies on the CSD, none of them have ever located this transition. And it's also worth noting that this transition is actually visible. So you can see this transition occurring, but it has no crystallographic signature at all. But when we run the CellVol code, as you can see up here, this is our network volume, so our occupied space within the crystal structure and our void space within the crystal structure down here. You can see that we get quite a clear change in gradient at this sort of reported transition range. And we have a very clear bulk modulus change as well of about 20 GPa at this transition. And so we can sort of see how this comes out immediately from the study. So we could run this CellVol code in about 20 minutes for all the pressures. And it sort of shows how, yeah, it's quite a cool method, I think. But within our paper, we also spotted similar discontinuities in 20 other published studies. So it's also worth noting this study that we stole these crystal structures from. So this was published on the CSD, and they didn't see any transitions at all, but were able to find it in their own data. And there's also 20 other studies we identified within the paper that we think there also might be further phase behavior in published studies that hasn't been seen before through general crystallographic analysis. So another sort of unique selling point we've been trying to push with our void analysis program, so the CellVol program, is an ability to calculate precision within our estimates. So it's a common feature in most void analysis programs that you tend to get a value without sort of any measure of the accuracy of that value. And so we sort of attempted to find a way of measuring sort of the accuracy of our measurements. So there's 2 sources of uncertainty in our measurements. So there's experimental uncertainty, and there's also the uncertainty from the calculation itself. So as a Monte Carlo process, so as we're putting random points within our unit cell, obviously we're going to have an inherent randomness to our program, and we're going to have a slightly different value come out every time. So there's a slight variation. And the way we get around this variation is by encouraging the user to run multiple runs. So this is the input box for a Mercury calculation. So you see the points per run and the number of runs. So we encourage a minimum of 3 runs to be run on the calculation, and with a defined precision can also be input by the user as well here. And so through running this sort of repeats on the same structure, we can see here, this is the error we achieved for glyphosate at ambient pressure. So I'll go on and talk about glyphosate a bit more later. And we can see that we achieved a 0.04% error, and that's relative to the network volume variation through these repeated runs. So of course, there will also be these experimental uncertainties, and these come from atomic positions, uncertainties in atomic positions within your CIFs. So obviously, if you have DFT structures, this won't be relevant for those. But we can propagate these into our overall calculation as well. So for this, we wrote a second Monte Carlo calculation, and this is based on perturbing each atomic coordinate with an independent Gaussian random number derivative based upon the standard deviations of each of the coordinates within your CIF. And it turns out if you get a fairly standard precision within an experimental structure, so a fairly well-resolved structure, you can then push it through. So the process, so for this process, we've produced 50 perturbed structures, so each with slightly offset volumes, each slightly offset atomic coordinates based on the uncertainties in the CIF. And we then ran the CellVol code on each of those individually. And we can see here this cumulative precision. So this is the experimental plus the calculation error, of course, because we're running the calculation of each of the structures. We find that comes out almost exactly the same as the calculation error. So we can see that the calculation error normally for a standard precision CIF is by far the significant error. And so this is the error we give within our calculations. Of course, if you've got a slightly more dodgy CIF, that might not be quite the same, but we reckon for most cases, this calculation error should provide a reasonable estimate. And so, as I said, yes, as before, so you can input the level of accepted precision in the calculation as well. So being able to break down the unit cell into this occupied and void space also means we can study the strengths of them separately. And so we can do that by fitting equations of state to the trends in the sort of compression of the data. So it also allows us to compare these to other classes of compounds. So first thing to note here is these are molecular solids at the top here, and these fall into a very narrow range of 5 to 20 GPa. And that's something I'm going to come back to in a little bit, because most structures studied at high pressure tend to be molecular solids. But also we can look at these other classes here, and if we compare network volumes, we see we get 40 to 150 GPa, and this turns out to be very comparable to the strength of metals. And so we can see that we're getting a fairly significant strength in these compounds. If we then compare this, so also this range of network volumes tends to be dependent on the class of intermolecular interaction in the compound. So in this histogram here on the left, this is non-hydrogen bonded compounds. We can see it's fairly flat and centers around 85 GPa, whereas for hydrogen bonded compounds, it's much more centrally peaked at 105 GPa, so much higher. Interestingly though, void volume varies over a very small range and is an order of magnitude smaller. And if we compare bulk modulus of networks and voids, we see this horrible swarm of bees. And so the inference here is no matter how strong the intermolecular interactions within a compound, or how strong the network volume is, the way it uses void space at elevated pressure seems to be sort of continuous across all these structures. So that's quite an interesting thing to come out, I think. So one of the other things we can do with these large searches of data, so I should have perhaps said all this data on this network, all this range of network and void volumes and all this data presented here, these all come from the extended searches of the CSD, running on all the high pressure CIFs in the CSD. So one of the other things we can get out of this is the packing coefficient. So this falls quite nicely here out of our calculation of network volume over total volume. And this sort of gives an idea of the occupied space within a crystal structure. And as you can see, as we move to higher and higher pressures, we move closer and closer to 1, showing how we were losing this void space. It's probably worth noting that these points very close to 1 at high pressures are probably more likely due to a misuse of ambient pressure van der Waals radii than truly being that close to 1. But an interesting point here is close pack hard sphere structures predicts a packing coefficient at 0.72. And also Kutaigorowski's work in the 1970s predicted that molecular solids very closely approximated close packed hard spheres. And we can see that appears to be sort of hold here. It also is very close to the range predicted by Gavasotti's molecular aggregation work. So that was using similar methods to the pixel method. And we can see here that he predicted between 0.6 and 0.8. And so we're again falling into a very similar range here. So doing some mathematical derivation, and I can share that later if anyone's interested, we can come to this equation here, which defines bulk modulus of an overall compound in terms of its relative contributions. And if we rearrange this by inputting our packing coefficient, we come to this equation here. And this puts bulk modulus in terms of network and void bulk modulus and the overall packing coefficient. And if we combine these typical ranges, as we can see here, 40 to 150, 2 to 5, and 0.6 to 0.8, we are able to replicate this range of about 5 to 20 GPa for the bulk modulus of molecular solids. And so it seems that because void bulk modulus varies over is an order of magnitude smaller than network bulk modulus, and because it varies over such a small range, and because K is proportional to the inverse of these quantities, because the void bulk modulus varies over such a small range, so do the bulk modulus of molecular compounds. So it seems that it's because of this void space always behaving in a similar way that molecular compounds are so similar in the range of bulk moduli. So that was all the data we had in the CellVol paper. So I'm now going to go on to some more current work. So based on this sort of process, we looked to do some more practical work. And so this was sort of for various reasons, for rounding out the thesis and also for giving us a way of looking at the CellVol code in situ. So being able to show how it could be used in the process of a high pressure study. So for this, we chose the compound glyphosate. So this is a phospho derivative of glycine, and it was recently studied in 2020 by Hollander et al., and it revealed 2 high-pressure Raman phase transitions. And so we thought 2 subtle high-pressure phase transitions that might not turn up so well in the crystallography. It kind of seemed like a perfect one to study with the CellVol code. And so when we look at the compression of this compound, so we were able to collect 17 high pressure points. And we can see the unit cell here fitted very nicely to Birch-Moynihan third order equation of state, giving a bulk modulus of 15 with a chi-squared of very close to 1. And as you can see here, through the unit cell, the normalized unit cell axes and the beta, there are no obvious signs of either of the transitions here, indicating that they occur without a discontinuous change in volume and therefore are by definition not first order transitions, so second order in nature. So again, backing up our theory that this would be a good compound to study here. So when we put it through the CellVol code, we can see these transitions became immediately obvious. So we can see here after an initial compression and hardening, the first transitions, which are placed here at the dotted lines signaling the transitions. So after initial hardening, we see the compression continues again after this first transition, and then a clear step up at the second transition, so in our network volume here. So following initial analysis, we noticed that we had a bit of a wiggling hydrogen down here, and so we decided to do some DFT on this compound. And as you can see, it becomes a bit harder to spot the second transition, especially after the DFT analysis, but there is still a clear change in bulk modulus of 58 to 85 to 91 GPa as we increase in pressure. So the transitions is clearly still there. It's also worth noting that the same complementary effects are also seen in the void volume, but because we have a much larger change in volume here, they're a bit harder to spot. We can also fit some relatively rough equations of state to the entire range of compounds, so they're normally second order fits because of the fitting across the phase transitions. But as you can see here, our network volume falls pretty much bang smack in the middle of that hydrogen bonded histogram at 105 GPa, and our void volume again is very typical of these kinds of hydrogen bonded compounds. So we then went on to look at our intramolecular energies, and I'm going to speed up a little bit here because I'm running a little bit short on time, but essentially the key thing to take away from this plot is there are a number of interesting things you can get from this pixel plot. So this is just a plot of the energies of the contacts within the first coordination sphere of the glyphosate molecule. So as you can see here, there's 13 in the nearest neighbors to the central molecule. But the clear thing to take away from this plot here is there is no clear discontinuities at either of the transitions in this intermolecular energy plot either. So again, without a discontinuous change in delta U, again, another first derivative of the free energy. Again, it's not a first order transitions for either of them. They look to be second order. So the first transition we were able to identify by an overlap in molecular surfaces. So as you can see here, up to the first transition, we see a fairly monatomic response from all the contacts, but when we hit the first transition, as you can see here highlighted, these 3 contacts fall away at a much greater rate. And these contacts 1, 5, and 8 are all related to be the closest to the central molecule. And it turns out that these are all related to overlap of molecular surfaces, which occurs at the first transition. And beyond this, there seems to be a reduction in end potential energy barrier, which is overcome you see this initial hardening, we overcome this energy barrier, and then these contacts compress at a much greater rate than the others. So the second transition, we were able to track down to an intermolecular effect. So if we look quickly here, we can see that these two contacts here, contact 2 and contact 7, were the only two to show this stepping up behavior, as we saw before in our initial CellVol plots. And we were able to identify them to be two contacts related to the central molecule by translations along the long axis of the molecule. And we were able to identify those by, as you can see here, the highest pressure structure in green and the lowest pressure structure elementally colored here. There is a hunching over of the molecule at elevated pressures, which mostly centers in this carboxylate group at the top here. And we're able to track this down by changes in torsional angles, which initially hardened before stepping down at the second transition. And these are due to both these torsional angles reduce the planar contribution of the sterics within the molecule. As you can see, as we step down at these transitions with torsional angle, we're able to initiate a much faster, so this is the second transition here, we're able to initiate a much faster compression in the intermolecular long axis of the molecule. So it's an intermolecular transition. So yeah, just to sum up, studying networks and voids individually can provide some very sensitive methods for studying subtle phase transitions, and these can allow accessibility to phase behavior that hasn't been previously accessible in crystallographic studies. So voids are much softer than networks, and these can be used to explain the narrow range of bulk modulated molecular solids. Also, high pressure has been studied. A high pressure study has been completed on glyphosate, and we've identified two phase transitions and identified their accompanying modes through the crystallography. And this is the first time they've been identified in this way. And so, although the stimulus study with the CellVol cohort here has been pressure, it is also equally applicable to studies at variable temperature and variable composition. So this is some more work I'm working on at the moment to raise some more phase behavior. So just a quick acknowledgements. I would like to thank my academic supervisor, Professor Simon Parsons at the University of Edinburgh, and my supervisor down at CCDC, Dr. Peter Wood. Please, both of you, take a photo within this century. I'd also like to thank the EPSRC for funding me, and the CCDC and the University of Edinburgh. Thank you all for listening. Any questions?
Dean, are there any questions? Yes, a round of applause. Well done. That was an excellent talk. Are there any questions from anyone? I certainly have one. We have got a couple of minutes. So, the question, I was actually quite interested in the packing plot. You showed a packing versus pressure plot quite early on in the presentation, and get that lovely sort of near sort of asymptotic type. Yeah, that one. That one. A lovely sort of asymptotic warmness behaviour towards packing coefficient, but it's quite scattered, and there are a number of outliers on there. Have you sort of gone back and done any detailed outlier analysis on the sort of the early range that have a very high packing coefficient and found out what's going on in those structures? Are they just errors, or are they? Is there something fundamentally interesting about them? What is it about those structures that means they're off the curve?
Yeah, so I think the first thing I'd like to point out is this is being a heat map. There is actually a very high density of points.
Sure.
This range, so they are quite rare. Looking back at them though, there is no clear, obvious reason why, and I think, to be honest, it's more to do with our use of van der Waals radii not fitting those particular compounds very well.
Okay.
So some that I've noticed especially are particularly ionic compounds. It tends to be that if we use ionic radii for those instead of van der Waals radii, the fitting tends to look a lot more classically, it falls more into that sort of thicker range there. So I think it's perhaps a bit of a misuse in those particular instances that could give that sort of anomalous behavior. But yeah, it's kind of a bit case by case in that respect of trying to work out why.
I mean, that sounds like not just that sounds like an opportunity to me to kind of come up with a better representation of conditional radii. So it's really interesting. Isaac's asked a question. He says, great talk. And then he says, how are you quantifying the changes at transitions? Some of the changes in rates seem quite subtle to the naked eye.
Yeah, so at transitions, we tend to look at bulk moduli changes. They are very subtle, and annoyingly, sometimes you get some really nice discontinuities and you do some DFT on it and disappear, which is not helpful. But yeah, so we normally look at bulk moduli as an indication of a change at a phase transition. So try and fit equations of state before and after the transition. And a sort of a change of more than about 10 GPa is potentially significant, but more than anything, they're indications of a need to go and find those transitions. Then I would be reserved about putting a plot and saying, oh, there's a discontinuity there. It's very subtle, but as a phase transition, I think it's kind of more of an indication of there could be something there. And that's, I perhaps have to rush over it on the last few slides, but you can then go down and try and find those transitions, and it becomes much more convincing.
Okay. Right. So thank you very much, Cameron.